Okay. So once we have this definition of computational indistinguishability, we can define a computational cryptographic object called a cryptographic pseudo-random generator. So we've gotten a little bit away from encryption, decryption schemes, but we'll get back there in a moment because it's a convenient time to talk about this notion of a cryptographic pseudo-random generator. In fact, one of the games in cryptography is to invent, not just, encryption schemes for sending messages, but other cryptographic schemes for doing all sorts of cool things like computing unencrypted messages and digitally signing messages and steganography and all sorts of other like fun stuff. And pseudo-random generators are, one example of a fun stuff that you might want to develop. Now, we talked already about pseudo-random generators in this course. I got another question. I'll get to it in 1 second. In the context of de-randomization, and it's the same definition, but with like different parameters and a different emphasis on parameters. So cryptographic pseudo-random generator has a different emphasis and a different sort of parameter range than the ones used for de-randomization. Let me jump back to this question. It was asked, could A composed with B be not probabilistic polynomial time though? Like B cleverly generates the exponentially rare input that takes a super long time. Perhaps it depends on what exactly you mean by meant by PPT. But generally, we set up the definition so that like, there's an amendment that says, I think that was ePPT. Yeah, generally we set up the definitions so that, this composition holds, like a composition of a polynomial time algorithm with a polynomial time algorithm is another polynomial time algorithm. For randomized algorithms, yeah, you have to be a little bit careful because you might be saying, are we talking about the expected running time or the max running time, or what are we talking about? For complexity theory reasons, the best definition is that you have a fixed running time, like 10n cubed, where your randomized algorithm always 100% of the time runs in at most that time, 10n cubed, no matter what the input is of length n. But it's still allowed to make random choices. That's the general definition of this most used definition of probabilistic polynomial time, and then it's clear that composition preserves this. Okay, good. So as you can see up here, we need one more piece of notation that's popular in cryptography. If I just write UN, that means the simple ensemble where the nth string, un, is just a uniformly random string of length n. Okay, so a cryptographic PRG is a pseudo-random generator. It's supposed to be a deterministic and also technically uniform, but a deterministic polynomial time computable function G that takes a string of length n and outputs a string of length L of n, and L of n should be longer than n. It's supposed to be, expanding seeds or short strings to longer strings. And we say it's a cryptographic PRG if it fools all polynomial time adversaries with exponential fooling probability. So we could really use the old definition with these parameter settings. To say it another way, it's to say that, okay, if you give G a uniformly random string of length n, it produces some kind of random string of length L of n, and that string should be computationally indistinguishable from a uniformly random string of length L of n. So these should look the same to all polynomial time observers up to like a negligible advantage. And okay, it's a basic assumption or slash conjecture in cryptography that cryptographic PRGs exist. In particular, the ones exist where the length is just n plus 1. So they just add 1 bit. This is a basic assumption that they exist. And I should say that, first of all, it's a reasonable assumption because there are some simple number theoretic candidates where, based on, presumed hardness of factoring or other tasks like discrete log. I'm not going to list them because I actually don't want to talk really about number theory in this lecture. But there's some simple number theoretic candidates that make people believe that these objects do exist. But it's certainly proving that such a candidate PRG really has this property, involves proving that there's no polynomial time algorithm that solves this certain task. And we're very bad at that, right? We cannot prove that P does not equal NP. So we don't really have a lot of hope to prove that a certain candidate PRG really is a PRG. We can only do it based on assumptions. And it's actually quite easy to show that assuming cryptographic PRGs exist implies that NP is not easy, that there are hard problems, that NP is not contained in BPP, probabilistic polynomial time. In fact, it also implies that P does not equal NP. Okay, so this assumption that there are cryptographic pseudorandom generators, which is like a basic tool you need to get off the ground in studying crypto theory, is a stronger assumption than P equals NP, does not equal NP, but we make it and move on. Of course, there's a lot of work towards understanding this assumption and maybe trying to weaken it, and we'll talk about that later. I should mention there's even a more fundamental difference here. I mean, way in which it's stronger, in the sense that to say that P does not equal NP is really about worst case problems. It's like saying that there's no polynomial time algorithm for SAT. And sort of intuitively, that's saying there's no polynomial time algorithm for SAT in the worst case. For every SAT algorithm, there's some input that it gets, polynomial time potential SAT algorithm, there's some input that it gets wrong. Generally in cryptography, you need much more, though, to get started. You need these sort of average case assumptions that are about like, well, algorithms, you're assuming that algorithms even fail to succeed, also known as fail. Algorithms fail even, let's say, with high probability on a random input. Okay, and so this, we don't really know. It's a stronger thing to say, there's a way to randomly generate SAT instances that are going to be hard for all polynomial time algorithms. That's quite a bit stronger than saying just, for any polynomial time algorithm, there will exist some input where it gets the wrong answer. Okay, but let's take this as an assumption, or for now, that there are cryptographic pseudorandom generators that stretch a random string by 1 bit, and they give you back an n+1 bit string that still sort of looks random for any polynomial time adversary. It's a fact, it's not too hard to prove, I'll sketch it, sort of, that if you make this basic assumption, then you can actually deduce a stronger assumption, that for all constants C, like 10, you can also have a cryptographic PRG that stretches n-bit strings to n to the 10-bit strings, length strings. Okay, and this is sort of the general thing that happens in crypto theory. You try to make a weak assumption that, okay, some weak object exists, and then, using smarts and things, try to use that as a building block to design a stronger cryptographic object. That's what's going on here. And I won't prove it, but the proof is not too hard. What I can give you is the construction. I just can't prove in this amount of time the fact that it satisfies the definition of a cryptographic PRG. But the construction is this. It's sort of by a picture. So imagine you have this picture here, G. It's supposed to represent like an algorithm or like even a circuit, but like say an algorithm that takes in n bits and outputs n+1 bits. It's the pseudo-random generator. And now we want to build a pseudo-random generator that takes in n bits and outputs like a lot of bits, like n to the 10 bits or something. So how it's going to work is you're going to take in your n bits, x, you're going to pass it through your stretch by 1 pseudo-random generator. That gives you an n+1 bit string. That's like this thing here. And you're going to take the very last bit, the n+1 bit, and like output it. That's this picture here. And you're left with n bits, that's these here. And then you're just going to feed them back into the pseudo-random generator and get like another n+1 bits. You're going to take the last bit again and output it. And then you take your remaining n bits and feed them again through the pseudo-random generator. Get n+1 bits, output 1 bit, take your next other n bits, feed them through the pseudo-random generator. And you just do this like as much as you want. Like you do this n to the 10 times, and that gives you an overall algorithm that involves running G n to the 10 times, it's polynomial time, and it spits out n to the 10 bits. And you have to prove, and you in fact exactly use the hybrid algorithm to prove this. You have to prove that, the n to the 10 outputs by this, bits output by this look indistinguishable from n to the 10 truly random bits to any PPT adversary, assuming the original seed was a uniformly random string. You have to prove that just using the assumption that like one step of the generator that goes from n to n+1 bits, outputs a string that looks totally random to a PPT adversary. I hope you might get the intuition for why it works. I mean, basically, an adversary looking at this picture can't tell the difference between like all these things output from G being uniformly random. But you have to take care because, you know, even in the first step, or in the second step, what you're putting into G is not a truly random string, but it's merely a string that is indistinguishable from truly random to a polynomial time observer. Okay. Great. So that's pseudo-random generators. I want to bring them up. And now we can actually get back to symmetric key or shared key encryption schemes. And I can make sort of a definition for weakening from perfect security to computational security for that. So cast your mind back again to Alice trying to send a message to encrypt a message, send it to Bob, and Eve is eavesdropping. So we say like such a scheme is computationally secure, and I've added another term here, single message, for reasons we'll get to. If for any two n-bit messages, M0 and M1, we have that when you choose a random secret key according to the scheme, and you make the encryption of M0 versus you make the encryption of M1. In both cases, you get a random ciphertext, and instead of demanding that these have identical probability distributions, we just demand that they're computationally indistinguishable. And here's a theorem that's about achieving this. And it assumes that you have cryptographic PRGs. So there's another example of taking, you know, one cryptographic primitive, a PRG, and using it to construct another primitive, symmetric key encryption schemes. So let's say you have a cryptographic PRG that stretches n bits to L of n bits. And as we saw before, even just assuming you can stretch n to n plus 1, you can convert it to stretching n to the 10. Then you can build a computationally secure SK encryption scheme for messages of length L of n, like n to the 10, using secret keys that are only n bits long. So the secret key generation scheme just is a simple one. You just draw a uniformly random string. That's the secret key, n random bits. But now, using this, you can encode, you know, n to the 10-bit messages. And how do you do it? It's basically you do the one-time pad, but instead of using a truly random one-time pad, you use the output of a pseudo-random generator. So Alice, when she's encrypting, she applies the pseudo-random generator to the n-bit secret key, gets back n to the 10 bits, and she's like, great, now I can XOR them with my n to the 10-bit message. And Bob knows the secret key. You can also generate the pseudo-random one-time pad, XOR it with C, and get back the message. And the proof that this is computationally secure is, you know, straightforward. In fact, I shall give the proof. So let's prove it. So we need to show that it's computationally secure. So we need to like fix any two messages, M0 and M1, and argue that this ensemble, the ciphertext for M0, is computationally indistinguishable from the ciphertext for M1. So the point is, for any message M and for a random secret key, if you look at the ensemble, the encoding of M by the secret key, okay, it looks like the ensemble where you XOR M with the output of the pseudo-random generator. And I claim that by the fact that G is a cryptographic PRG, this is computationally, sorry, I said that wrong. Simply by the fact that the PRG G is an efficient algorithm, I claim that this is indistinguishable from, okay, there's a typo here. This should say L of n. Okay, it's indistinguishable from, sorry, because G is a pseudo-random generator, I've sort of botched this explanation. We know that G applied to the secret key is indistinguishable from a truly uniform string of length L of n. So the PRG property shows that these two boxed things are computationally indistinguishable ensembles. Now I claim that the whole parenthesized things, where you take the box things and XOR them with M, these are also computationally indistinguishable. And this follows from our little lemma from before that said if you have two computationally indistinguishable ensembles and you apply the same deterministic algorithm or same algorithm to both of them, you preserve computational indistinguishability. And that's what we're doing here. We're applying the little algorithm that XORs the string with the message. Okay, so the PRG property gives us this. And now it's a fact that for any fixed string M, if you XOR it with a uniformly random string, that's exactly equal in distribution. It's 100% indistinguishable from a truly random string. Okay, so that shows that like every encoding is computationally indistinguishable from a truly random string. So all pairs of messages have indistinguishable encodings. Okay, I hope that was clear. If you have any questions, do ask. Okay, so let's review. This is kind of cool. We're happy because now we have a scheme where the length of the keys can be much less than m. You know, the key length can be n, and you can encode messages of length n to the 10 or n to the 20 or anything like that. That's nice. Still very bad to use it more than once, though. This is still like a one-time sort of thing because you still have this property that you know, once the secret key is fixed, the pseudo-random generator is deterministic. So the sort of long pad that you get out of it is fixed once the secret key is fixed. And so if you encode multiple messages, you're going to encode them with the same pad. And so you'll still have the property that, like, you know, Eve can take two ciphertexts, XOR them together, and she'll get the XOR of two plain text messages. And that's very risky for cryptanalysis purposes. Now you might say, oh, here's a cool trick for getting around that. Whenever Alice, you know, is going to send a message to Bob, she takes her message that she's going to send, and she appends to it a new freshly generated secret key. And she encodes the message plus the secret key, sends that to Bob, and that's fine. And now Bob gets the message, he can decrypt it, he gets the message, and he gets like a new secret key that they can agree on. And so now they can, you know, do their next message with the new secret key. And so we don't have this one-time issue. That's true. It's a cool trick, and you can use it. But still not like the awesomest thing in the world because it's kind of stateful. Like, you know, if Bob like misses one message, then he's totally out of luck for getting the rest of the messages. So yeah, it's not ideal. It's better than nothing though. Let me end by saying that I mentioned that this kind of security is called single message computational security. I won't get into more detail, but there is a better security notion for encryption schemes. It's called this indistinguishable under CPA, chosen plaintext attacks. I won't define it formally, but it's kind of the gold standard security desire for cryptographic schemes. And it basically means not just, you know, if you're going to send one message, it should look, the ciphertext should look indistinguishable to an adversary. You want to support like the ability to encrypt polynomially many messages in security parameter. And you also want to allow a very powerful adversary who can sort of request Alice give the encryption of some messages. So like the adversary says like, Alice, why don't you, or she maybe tricks Alice into like encrypting a bunch of messages, and maybe in that way tries to learn something about the secret key. But then finally you measure like, okay, for maybe the true messages that Alice wants to send, you know, we measure whether Eve can get any advantage in distinguishing them. Okay, so I didn't really explain it formally or even maybe that well, but I mentioned because it's sort of the more general gold standard of what you want for an encryption scheme. And let me just tell you, I mean, now we get into more sophisticated results in cryptography theory, which I won't even try to sketch. But it's known that you can get a symmetric key encryption scheme with this very good, you know, sort of gold standard notion of security, indistinguishable against chosen plaintext attack, provided, not provided that PRGs exist, but provided this other crypto object called cryptographic pseudo-random function generators exist, which is, well, a stronger looking object. But I'll just tell you another fact, and this is like another theorem in cryptography that we will not prove, but it's a good theorem. It shows one of these construction things that like just starting from a pseudo-random generator, you can construct pseudo-random function generator. And therefore you can construct symmetric key encryption schemes that have this great security property. So again, this is like just telling you about this story of like, main tasks that go on in cryptography theory, starting from a weak assumption about pseudo-random generators, you show you can get the stronger things, pseudo-random function generators, and then you can get symmetric key encryption with like these great properties. That's sort of the name of the game. So I've told you how you go from pseudo-random generators to at least single message secure symmetric encryption schemes. And then I told you can in fact get the IMCPA one from PRFs, and PRFs you can get from PRGs. There's like a most famous theorem in this area called the Hill Theorem from 1999. It stands for the author's surnames, Hostad, Impagliazzo, Levin, and Luby. And they showed that you can get this object pseudo-random generator just assuming you have this weaker looking object called one-way function. OWF stands for one-way function. And this is basically sort of the end of the line going, leftward. In the sense, this is sort of like the weakest, this is basically like the weakest object that people are willing to assume exists. And people are willing to assume it exists, but luckily, like, all these chains are known about how if you just have a one-way function, you can get all sorts of cool stuff. So let me quickly give the definition. A one-way function is a function that maps strings to strings. Perhaps you've even heard it before. It should be an efficient compute function and deterministic. And it should basically have the property that, although it's efficient to compute it, it's very hard to invert it. So basically, you want to say that for every PPT adversary A, if you pick a random string x, apply f to get the output, f of x, and now you ask the adversary, okay, here's f of x. You just ignore this one to the end. Basically, you just have to also tell the algorithm what n is. Here's f of x. You don't have to find x, but just please tell me any y that has the same f value as f of x. So the A gets this f of x, and it's just got to find some y where f of y is the same thing as f of x. And we assume that f has this property, it's hard to invert, that no PPT algorithm can do this with better than negligible probability. Okay, so this is the definition of a one-way function. There's a question. If they're weaker objects, is it possible / easier to generate PRGs and one-way functions from a pseudo-random function generator? Yeah, so generally, this direction is always sort of easy and almost like from the definition. So in fact, all these are equivalences in the sense that assuming one exists, you infer that the other exists. But like this is always the direction of difficulty. And like going from here to here is almost like by definition. I should say, I said this was the end of the line, but I can go you one further. There's even something called a weak one-way function, where you just weaken this. Instead of saying negligible chance, you allow them to just not be able to do it perfectly. They can't do it with probability at most 1 minus 1 over n to the 100 or something. But there's even a construction that goes from weak one-way function to one-way function, and I can even tell it to you because it's kind of easy. Let's assume that f is a weak one-way function. So it's easy to compute, and it's like slightly hard to compute preimages for it. Well, you build a new function g, which takes m strings, and g on these m strings x1 through xm is just the string gotten by attaching together f of x1 through f of xm. And so now the task, it's easy to compute g because it's easy to compute f, but to invert g, you're given like now you're given like a bunch of strings, and you can set m to be n to the c plus 1, where this is the same c here. The task is now you have to like sort of simultaneously find preimages for all of these things. And so if it's slightly hard to find one preimage, then it's going to become super hard to find simultaneously preimages for a bunch of strings. So I said that kind of fast, but maybe you can imagine how this construction and even proof goes. Okay, but this Hill theorem is actually very difficult, and that's why it's sort of a famous theorem. I can even tell you, on the subject of one-way functions, a candidate one-way function. It's not people's most cryptographers, like serious cryptographers, most favorite candidate because A, it's kind of inefficient, and B, not so convinced of its security, but on the other hand, nobody knows how to break it. And the candidate one-way function is, the inputs are n strings of length n, and you think of these strings as numbers, mod 2 to the n, plus s, a subset of the numbers 1 through n. So overall, you have n squared plus n bits in the input. And F's output, you just output the same strings, and together with the sum of some of the strings, namely the ones in the set S. And you do it mod 2 to the n. And so this is certainly easy to compute, but going backwards, if I give you, it's very much like the subset sum problem. Like I give you a bunch of n-bit numbers, and I give you some number which is achieved as like the sum of some kind of subset of them. And the idea is that perhaps when the numbers are random and the ones that you secretly added up are also chosen randomly, it could be hard for an algorithm to figure out what that set is. So this might be a one-way function. And so it's why you might believe that one-way functions exist. And once you believe that, then you get all this other stuff as well, thanks to previous work of cryptographers. So you can get a lot of crypto primitives out of one-way functions thanks to a lot of work of cryptographers, like symmetric key encryption, digital signatures, all sorts of other things. But not everything. At least it's not known how to get all the things you would want. And one thing that it's not known how to get is public key encryption, which is that thing that RSA solves. So we have this very minimal assumption one-way functions that get us a lot of stuff, but it's not known whether it gets you public key encryption. And there's a very famous paper in the theory of cryptography and average case complexity by Impagliazzo. It's called A Personal View of Average Case Complexity, but it's from '99. He famously introduced his so-called 5 worlds of like what might be possible about average case complexity, hardness, and easiness. And one of the worlds is like the world where P equals NP, and like everything is easy, and there are no hard problems, and there's no cryptography. But 2 of them are called minicrypt and cryptomania. And minicrypt is the world where one-way functions exist. And so you get like a lot of cool crypto primitives, but not all the ones we know. And cryptomania is like another world where public key encryption exists. And we don't know which world we're in, but we actually kind of believe we're in this world because we do have some schemes for doing public key cryptography like RSA. But these are 2 distinctions that need to be kept in mind. So I mentioned that because it's a pretty famous paper in complexity and